You're welcome to Maths 420. We're now in the second video and the second video for the second chapter with topic character, group characters. Okay, so we continue from where we stopped. In the previous video, we had seen Shaw's lemma. We had seen in one of the lemma for we had seen Shaw's lemma, and we had also seen the property for a lemma for Mascage theorem. One of the lemmas, we learned how to construct a particular matrix labeled C, which was equal to a matrix with entry Z. Zi is taken from the field K. Okay, so we're going to continue from there. Okay, because we will need that knowledge in this particular proof question. So it says show that the coefficients of AX are an irreducible representation of degree f. Take note of its degree. That it satisfies this inner product. Don't be scared of all the deltas you see. You will see us prove it. Okay, so now what we want to do is we consider the fact that AX is irreducible, its degree is f, and once we have this irreducible property of f, we want to do things like inner product. Just remember immediately the fact that we can construct a C of this one. Okay, so now during the exam or test, don't tell me previous solutions. Rather, show me how. Construct this inside this particular part of the proof. Okay, construct this C. Okay, and make sure it satisfies this condition, and then call the lemma, the corollary of Shaw's lemma, and state it. Okay, so you will need to construct the C just like you know how to construct it now, and then show that it satisfies this condition. After showing that it satisfies this condition shows that we have commutativity, right? You now state Shaw's corollary of Shaw's lemma, and that states that if AX is an irreducible matrix representation over an algebraically closed field K of group G, then only matrices that commute with all matrices AX are the scalar multiples of the unit matrix. So this, once you get the matrix, it must be the same thing as the scalar multiples of the unit matrix. Oh, that means that our C, because C commutes, as you can see here, because C commutes must be equal to the scalar multiple of the unit matrix. So scalar multiple of the unit matrix IF, because our AX is of degree F. Okay, AX is of degree F. That's why it's called I with respect to the degree of A. Okay, so now we know what C is based on the corollary of Shaw's lemma, but we're not true. Our target is to show an inner product that will satisfy a certain condition. Now, using C will lead us to what we want, but first we need to find what K is. We know what C is. It is this. We need to find K. So how do we find K? We simply take the trace of both sides of our equation, of this our equation asterisk, okay? And it is this, okay? Okay. So if we take the trace of C, so we take the trace of both sides, because whatever you do on the left, you must do on the right. You find that the trace can be written as this because C is this from our previous, from the constructed C, right? In terms of A, in terms of E, and A again. And K is out. Why? Because it's a scalar. So the trace can go on IF. Now, everyone, what is IF? IF is the identity matrix, right? And A is an F by F matrix, right? So how many ones, or every other thing here is 0, every other thing is here. So how many F's are here? How many ones are here? Definitely F of them, right? Because it stops at it's an F by F matrix. So there are F of them. So if you sum all of the F's together, what will you get? Sorry, all of the ones together, you get F, right? F of them. So that's why we got F. Okay. So that's how we got F for that. That kind of settles that. Okay, so we know what the trace of IF is. It is F. So let's see what we do. So the right hand side of this equation is just going to be kf, so kf will keep following us all the way. But let's see what to do to the left hand side. For the left hand side, the trace can go into the sum over g, y or g. The trace drops inside nicely, as you can see here. And associativity allows me to do what I've done here. Let's link these two together and leave the ay out. And because the trace of AB equals the trace of BA, I can interchange E and AY inverse, okay? Again, using associativity, I can bring out the E and let A inverse AY come together. So the trace is on my E, as you can see there. However, because AX is a representation, my left-hand side changes to this. Can you see? I can do this. My right-hand side continues to remain KF, as you can see there, okay? But you know what AY inverse Y is. It's A1, which is 1. That we had shown at the very beginning of this Maths 420. Okay, so again, you can see, because it is I, what happens? Everything here goes to 1. So we just have trace of E times equal to KF as is required. But then the sum is over what? G, Y and G. Now, G, what's the order of G? The order of G has always been small letter g, right? From the beginning, even for all this while in the lecture. So it's the same g we're using all through the lecture for 420, unless specified otherwise, okay? So because there are g elements in G, the trace, once you're summing all the y's, would definitely be G. There'll be G of them, okay? And the trace of E remains as it is, okay? Now, this is equal to KF, and we have satisfied this condition. So if I make K subject of formula, because we're looking for K, remember, just divide both sides by F, divide this N by F, this F will cancel this F, we're left with G over F times trace of E, which is what you see here as asterisk, asterisk. Now, from our previous generation, when we're constructing C, we had specified what E was. It's of this form, and these elements are taken from the field K, right? And if you recall that a representation is of degree F, right? And its induced matrix is Bx, right? And Bx, we were able to see that it can be represented as Cx0 dxEx. Remember? Now, this our E, you can see it here, is a subset of the representation Ax of degree F. So it means that our maximum degree or degree of E will be what? F, okay? So with that said, what would be the trace of E? E, we know now, is a matrix with entries Z11 all the way to Z1F, go down to Zn1, all the way to ZFF. Remember, this is 1, 1, right? So if you're summing, that's a trace. Trace is the sum of diagonal, right? So that's how we got trace of E to be. So this is E. That's how we got the trace of E to be this. Okay. So now we know what the trace of E is. So the trace of E we have found. So, but we know what K is. K is this. And we found the trace of E, so we just substitute back trace of E. And trace of E, which is this, again, K is this, trace of E, substitute back. So we have this relationship. Okay, so we found K. But what was asterisk? Asterisk was the product, well, was C equal to the scalar times the scalar multiple times the unit matrix, okay? So let's go back to where we stopped. We found K. We want to substitute back in asterisk. So substituting that value of K into asterisk, we'll get this relationship here, because you know what K is. All of this is K, and it's times the unit matrix, okay? But what is C? C was that matrix which we constructed, which we had stated earlier. So whenever we see C, we put our value there, and our left-hand side, so right-hand side remains right-hand side. But then you know what A is. A is that matrix in the form A, Ij, right? And you know what E is. Okay, so we just substitute them back as their matrix form. Our target is to find that inner product, remember? Okay, so the value of A, E, and A are substituted nicely there, and our left-hand side, so right-hand side remains as it is. Now, by definition of orthogonality, the property of orthogonality of characters, it says that the sum of the product of elements of our matrix representation over our group G is 0, on the condition that they do not match. So if they match, it wouldn't give us 0. If they do not match, you will get 0. So we have two cases before us, when it matches and when it does not match. So we succeeded in bringing ourselves up to this point. But we have a situation. We want to show that our product, the inner product, will give us a certain value with deltas all over it, remember? So we have to consider the two cases. So to get the two cases, we check the first case, if they match. So if they match, what does that say? When they do not match, they become 0, right? By the orthogonality property. But in our own case, we want to start with if they match. So we're checking if they match, this is what we would get. So if they match, our equation, all of this is what I've brought forward here. Okay, so our equation, this. The summation sign is over terms in y, right? Okay, and we have, there's a z down here. Remember what z is. The I, J, and P, Q, they're all matching, meaning they're the same all through. So it means I can get the sum right here. Do you agree? For our Z, J, J, right? So that's how we got this out of the equation, and the sum of A and the A's all together right here. Okay, we're not going to simplify more than that. We're just going to leave it as it is there. And we have this, my right hand side remain as it is. But you can see something. This will cancel out with this, right? If you divide through on both sides, right? So if I bring that out, I'm left with just this and this and this, right? But what is this times I? Identity matrix times G over F is just G over F, okay? And this remains as this, so this is here, okay? So that's how we got the equation you see there for our first case, when they match, okay? So when they match, we'll have this relationship. I like that we can see the A's because that's what we wanted earlier on. If you remember the question, the questions have it that we're having inner product, okay, AG, PQ, okay. So let's just continue. We'll explain everything as we go. So we didn't cancel them out. That's on the grounds that they match. That's why that relationship satisfied what we had. Okay, so when they match, we have this relationship when they match. However, if they do not match, what happens? Well, then this product, this thing must be equal to 0. That's what it says by the orthogonality property, that it will be 0. Okay, so this relationship goes to 0. Well, with this, as you can see there. So with that, we have two solutions. The first in this form, the second one in this form. So how do we write a general equation for them? Solution that will handle that. Now, you had seen this definition earlier on, okay? We have the phi and the psi product, okay? And it's given as this. You know that. If you don't, check your definitions, you will see the definition for the inner product of these two characters. Okay, so if we happen to have this to be so, and we're able to show this relationship to be this, okay, it means that I can write what this sum is 1 over G with phi of x, psi of x inverse. So look at this. I have aij of y inverse, apqy. I'm trying to find a relationship with them. It means that if this is this, how can I make this without the 1 over g? It means that I have g into phi comma psi will be equal to the sum over phi of x and psi of x inverse, right? Okay, so that's what we're trying to find the relationship for. So how would this look like when I compare with this? Okay, so I'm looking at this sum and I'm comparing with this sum. So by the time you compare it, you will get what we have here. So you can look at it carefully and see if it follows so. Okay, we just compared the two definitions. So we brought this one because that's our question. That was our question from the very beginning, and I try to relate it with this. Okay, based on what we've gotten thus far to this point, all our solutions here, the two solutions, these two solutions, we want to generate a general solution. And so to get the general solution, we happen to have that this guy here is this. So meaning that let me clean this. For this case, we have seen that all I need to represent it is this G. So this G times inner product, I can replace this entry here, okay, which was our solution before. Remember, we had two, when it is not matching and when it is matching, okay. So that's how I got this equation here for the one when it is matching, okay. So when it is matching, it satisfies this. When it is not matching, we had another value, and the value was equal to 0. Look at it here. And there's a sum in ZPG there. So how do we bring it in? So this is what we'll do. We simply write it as, so for this, as it is right now, you can divide through or multiply through, divide through by G. Divide through by G. So this will cancel out, this will cancel out. So that this inner product, IJ, A, P, Q, is same as 1 over F, okay? So if this is 1 over F, I can put this delta sign in this form, IQ and JP. How? Whenever I is equal to G, this thing goes to 1. Now, I equals to G means that I'll get 1, 1 here. Now you'll be wondering, what of the PQ? Don't worry. Once I and J are the same, when I get to P and Q, what happens to them? They will become the same. I keep counting 1, 2, 3, 4, 5, 6. Till I get to P. When I'm at P and Q are the same. So it just becomes the same thing as the equation we're looking for before. You understand now? So it's like counting 1, 2, and then there's P somewhere. And you're saying that P is equal to Q at this point. For whenever they're the same, you get 1. So at this point, when I get to P, this equation here will become A, P, P, A, P, P. Okay, P, P, because, and then this will give me 1 over Q. Okay, sorry, 1 over F. Okay, so because once it becomes equal, our delta symbol allows us to make it become 1 when they're equal. And if they are not equal, what happens? We'll get 0. And it will satisfy this equation right here, okay, to satisfy this. So that's a general equation, and that completes our proof, okay. So if it was a little clumsy and you didn't understand it, you can ask me questions or go through it slowly and also try solving and see if you get it. Again, we got to this point. I haven't solved these two conditions nicely. We needed to generate a general solution, and we use this definition for the inner product of two characters and related it to the given question. Our given question needed us to find AIJ, APQ, the inner product. And we see that if you want to compare this we want to compare this to this product. We will need it to look something like this side. And we saw that, oh, that's simply saying AIJ inverse, Y inverse, and APQY, okay? Summing over Y in G, okay? Because it's in Y. And then relating the two solutions, this one first, because it's the one that has a value in front, and substituting, we now saw that we could use our delta values for when delta ij is when I and j are equal and when they're not equal, and we saw that it will satisfy the condition as given in the proof, and that's the end to the proof. Next question before us says that we should state and prove the theorem on character relations of the first kind. So we need to be able to state it and also be able to prove it. Now, what does it say? It says that when I have chi of x and chi prime of x, and that they are characters of x, characters of irreducible representation, ax and bx respectively, then chi prime is equal to 1 when a and x are equivalent, and 0 if a and x are not equivalent. Okay, so that's what the character relation of first kind states. So you need to be able to state it, you need to be able to write it yourself. Okay, so if you happen to have a and x, ax and bx irreducible representations, then the inner product of the characters of these two matrices, if they are equivalent, you will get 1. If they are not equivalent, then it will be 0. So how do we prove that? So we start the proof. Okay, so since these two characters are for ax and bx, and they are irreducible representations of degree f and h respectively. How do we know that? Because earlier on in the first video had given us these definitions, and I said I needed us to stick to it, if you remember. So these are the definitions. This one is of degree f for a and degree h for b. Now, we know that is their definition, and it means that the character for A would look something like this, and that of B would look something like this, noting their degree, right? Okay, and you know what character is the sum of the diagonals, right? That's a trace of the diagonal. Okay, so the first case we'll need to consider, because that's what the question, the theorem states. It says that when it is equivalent, you get 1. If they're not equivalent, you'll get 0. So we have to check the two cases. So the first case is when they are inequivalent. Wow, when they're inequivalent, it claims that they will be 0, right? Okay, so let's see what happens. Would that be true? So when you have the inner product, you get this 1 over g. Let me go back to that definition. We had seen the definition somewhere. Look at the definition here. We're using the standard definition, which is a definition you should know by now. Okay, so we're using this definition. So if we happen to have the inner product and they are not equivalent, so you get this definition. So if you get that, we know what the chi of x is and chi prime of x inverse is. It's simply working with a, look at it here, and that of b, right? So if you do the product of the two of the inner product of the two of them, and they are not equivalent, what did we get from the previous theorem? It says that when they are not equivalent, what happens? It will go to 0. See there? So definitely our answer here is 0. What if they are equivalent? So if they are equivalent, we will have this product, as we can see here. They are equivalent, and so it will satisfy that condition. And what does it tell us? It says that it is equal to, so I'm going to far. It says it's equal to 1 when they are equivalent. They're equal to 1. So automatically we get our relationship here, and there we have the sum 1 over f, and this will be equal to 1 because there are f of them. Remember, they're the same. Okay, so and the proof is complete, and that is that to the proof. And thank you.